Hello, my name is Vincent Van Buren, and I am a member of the faculty in the Clinical Translational Medicine Department at Texas A&M College of Medicine. This video is about screening for disease key biostatistics concepts for Step 1. Screening tests help physicians detect the presence of disease, and screening tests have their efficacy measured against a gold standard. A gold standard test measures the actual presence of a disease or the actual absence of a disease. And a screening test under consideration will either test positive or test negative for disease. The correct test of positive for when disease is present are referred to as true positives. So this would be a count of subjects that test positive for the disease when disease is actually present. Likewise, a true negative is when disease is actually absent and the test produces a negative result. So these counts in these boxes in a truth table would represent the accurate results of a test. When the disease is present and the test produces a negative result, that's referred to as a false negative. When disease is absent and the test produces a positive result, that's referred to as a false positive. Sensitivity and specificity are two measures of test performance. Sensitivity is the number of true positives divided by the total number of individuals where disease was present. So that total is equal to the number of true positives plus the number of false negatives. So sensitivity then is equal to the number of true positives divided by the sum of true positives plus the false negatives, or the sum of this column. That represents the sensitivity of the test. The specificity of the test can be computed as the number of true negatives divided by the total of false positives plus true negatives. So the number of true negatives divided by the total of those subjects with disease absent. Sensitivity can be defined as, given that disease is present, sensitivity is the probability of obtaining a positive test result. And specificity, given that disease is not present, specificity is the probability of obtaining a negative test result. The best tests will have both high sensitivity and high specificity. For a given test threshold, the specificity and sensitivity are stable values of the test. Sensitivity and specificity are not affected by the population with the disease or the condition. So these are properties of the test for a given test threshold. Whereas sensitivity and specificity are qualities of the test, measuring the performance of tests, the PPV and NPV are post-test probabilities that are of interest to physicians for assessing the likelihood of disease when a patient tests either positive or negative for disease. The PPV, or positive predictive value of a test, is equal to the number of true positives divided by the total number of patients that test positive. So that would be the number of true positives plus the number of false positives. So again, the PPV is the true positives divided by the total of true positives plus false positives. Likewise, the NPV, or negative predictive value, is the number of true negatives divided by the total number of patients who test negative, the number of true negatives plus false negatives. Positive predictive value. Given that a test is positive, the positive predictive value is the probability that disease is present. So if a new patient test positive, you can compute the PPV for that patient to determine what their probability of disease is. The negative predictive value. Given that a test is negative, the negative predictive value is the probability that disease is not present. Higher prevalence makes PPV higher. So whereas the sensitivity and specificity of a test are properties of that test, PPV will be affected by the prevalence of the disease or condition in the population. Lower prevalence makes PPV lower, and prevalence, once again, does not affect sensitivity or specificity. Here's an example. Suppose there is a test for diabetes, which is a common disease, and a test for ACTH deficiency, which is a rare disease, where both tests have a specificity of 90% and a sensitivity of 90%. So the quality of these tests are equivalent. If patient A tests positive for diabetes and patient B tests positive for ACTH deficiency, patient A will have a higher probability of actually having the disease present because of the higher prevalence of diabetes. And this is a property of how prevalence changes what PPV is. The double hump graph is commonly seen on the step 1 examination. In these graphs, the value of a test measurement is represented along the x-axis, and the number of patients is shown along the y-axis. The first part of this graph shows a healthy population. And this second part of the graph shows the disease population and how they each relate to the test measurement. So as you can see, for this particular example, the test measurement for healthy people has a low value. Test measurement for disease patients has a high value. And there's no overlap in those populations. So in this extreme example, it's very easy to decide on a test threshold. If we drew our test threshold at this line, then values above that measurement we would consider positive test, and values below that measurement we would consider negative test. And we would be correct 100% of the time. A more realistic situation looks like the graph below, where the healthy population and the disease population are overlapping along the test measurement. So here we have very many true negatives that fall below this threshold line, very many true positives that fall above it. But there is some overlap. So we see some false negatives here. These are patients who have the disease but test negative. Likewise, there are some false positives. So there are some healthy persons who do not have the disease but test positive. Let's ask a question about this. Which test threshold will maximize the sensitivity of the test? So before we chose threshold B, because that most cleanly divided it into healthy and diseased patients. But we could choose other thresholds depending on our desire to maximize sensitivity or maximize specificity. So which one of these, A, B, C, or D, will maximize the sensitivity of the test? Pause your video for a moment to consider your answer. So the answer is threshold A. Sensitivity is the number of true positives, given here, divided by the total number with disease. If we choose threshold A, then everyone with the disease will have a positive test. So there are no false negatives shown anywhere in this graph, because all the persons with disease are accounted for above threshold A. So with false negatives at 0 and sensitivity equal to true positives divided by number of true positives plus false negatives, with this at 0, that simplifies to the number of true positives divided by the number of true positives, so that will always be equal to 1. Another type of graph often seen on the Step 1 examination is the Receiver Operating Characteristic Graph, or ROC graph for short. ROC graphs are a way of comparing different screening tests. They plot sensitivity and 1 minus the specificity, where sensitivity is also called the true positive rate, and 1 minus specificity is also called the false positive rate. Tests with curves that come close to the upper left corner, like A, have a high true positive rate and a low false positive rate. Those are the best tests. Tests with curves close to the diagonal are poor tests, like C. As we get closer to the diagonal, those become poorer tests. And those at or below the diagonal are completely worthless. So a test along this line or below this line would have no value as a screening test or diagnostic test. And just to reiterate, in this example, test A is the best, test B is the next best, and test C is the worst test based on this graph. That concludes this video. If you have any questions, please email me at vanburen@tamhsc.edu. Thank you for your attention.